Ever get that feeling like you're stuck in a never-ending A/D test?
Yeah.
Like just constantly trying to figure out which button color
Right.
or headline is actually going to get people to click.
Yeah.
It's, well, you're not alone.
No.
This is like a classic problem
Yeah.
in data science and machine learning
Yeah.
called the logistic bandit problem.
Right.
And today,
Yep.
we're diving deep into a paper
Okay.
that tackles this challenge head on.
Okay.
It's called An Information Theoretic Analysis of Thompson Sampling for Logistic Bandits.
This sounds very technical.
It does.
And it's really about making smarter decisions
Yeah.
when you have limited information.
Right.
So imagine you're
Yeah.
a company showing ads online. You want to maximize clicks,
Of course.
but you don't know which ad is best for each user.
Right.
You have to experiment,
Yeah.
learn, and adapt on the fly.
Right.
It's a very dynamic situation.
Yeah. And this paper focuses on a specific algorithm called Thompson Sampling,
Right.
which seems to be pretty good
Yeah.
at solving these kinds of problems.
So Thompson sampling is like
Okay.
imagine you have a bunch of slot machines
All right.
and you don't know which one has the best payout.
Right.
You try each machine a few times.
Okay.
You kind of form a belief about which is best.
Okay.
And then you use those beliefs to guide your future choices.
So you're constantly balancing
Right.
exploration,
Exactly.
trying new things, with exploitation, sticking with what seems to be working.
Yeah.
I guess the big question is, how can we guarantee
Yeah.
that this approach
Right.
won't lead us down a rabbit hole?
That's a great question.
How do we know we're not wasting time and clicks
Yeah.
on ads that just aren't going to work?
That's where the concept of regret comes in.
Okay.
Think of it as the opportunity cost of learning. You're figuring things out as you go, so you'll inevitably make some choices that aren't ideal.
Right.
The goal is to minimize that regret,
Okay.
to ensure that Thompson sampling doesn't lead to too many missed opportunities.
Okay, so minimizing regret is the goal.
Exactly.
But how does this paper actually help us do that?
So the paper
Yes,
introduces a really clever way to analyze and bound the regret of Thompson sampling for these logistic bandit problems.
So this means we can guarantee it won't do too badly,
Exactly.
even in the worst case scenario.
Worst case scenario. Yeah.
And it does this by focusing on something called the information ratio.
Yes.
Information ratio. That sounds intriguing.
It's all about balancing
Okay.
how much information you gain about the problem versus how much regret you risk incurring at each step.
Okay.
Think of it as a trade-off between exploration and exploitation.
So the more you explore,
Right.
the more information you gather.
Exactly.
But you also risk making
Yes.
more suboptimal choices
Yeah.
in the short term
In the short term.
to win in the long term.
Exactly.
Right. Yeah.
And the paper
Yeah.
proves something really important about this information ratio.
Right.
It establishes a bound, a limit, that only depends on the dimension of the problem,
Okay.
not on the number of actions you can take.
So wait, what does dimension of the problem actually mean in this context?
So it's essentially the number of unknown factors that are influencing the outcome.
Okay.
Think of it as the complexity of the situation.
Okay, so if I understand this correctly,
Yeah.
the paper is saying that even if the problem is super complex
Yes.
with tons of variables,
Yes.
Thompson sampling can still handle it efficiently.
That's the key takeaway.
Wow.
It can find that sweet spot
Yeah.
between exploration and exploitation without getting overwhelmed by too many options.
It's great.
But there's one more layer to this.
Okay.
A little bit of a technicality.
Oh, I love technicality.
Okay, good.
Lay it on me.
So the paper specifically focuses on logistic bandits.
Right.
And in these scenarios, the probability of success, like the probability of someone clicking on an ad, is determined by a special function with a parameter called beta.
Beta, all right.
Yeah. And previous attempts to analyze regret were really sensitive to this beta.
Okay.
They didn't work well when beta was large.
Oh, really?
But this paper breaks through that limitation.
So it's like they cracked some kind of code, figured out how to make Thompson sampling even more robust.
Exactly.
Yeah.
They proved that the regret bound is only logarithmic in beta.
Okay.
Which is a huge improvement. It means Thompson sampling can handle situations where identifying the optimal choice is actually easier.
Wait, hold on.
Yeah.
Easier?
Yeah.
I thought a larger beta meant a steeper curve.
Right.
A more drastic difference.
Right.
Between good and bad choices.
Correct.
Wouldn't that make it harder to find the best option?
It's counterintuitive, I know.
Yeah.
But think about it this way.
Okay.
A steeper curve means there's a clearer distinction between near-optimal and suboptimal actions.
Okay.
You get more bang for your buck with each experiment.
I see.
The fact that the regret bound is only logarithmic in beta reflects this.
Okay.
It shows that this improved learning speed translates directly into better performance.
Okay, so a steeper curve is actually a good thing in this case.
Yeah.
It gives you more information with each experiment.
Right.
Allowing Thompson sampling to hone in on the best choice.
Exactly.
More quickly.
Yeah.
But this all sounds a bit theoretical. How does it actually play out in the real world?
Well, that's where it gets really interesting. This paper isn't just about abstract math.
Right.
It has real-world implications.
Yep. Okay.
It means we can use Thompson sampling with more confidence in a wider range of applications like online advertising, recommender systems, clinical trials, and even A/B testing for websites.
So it's like a Swiss Army knife for decision-making.
It is.
But you mentioned earlier that the paper focuses on a specific condition.
Right.
For these results to hold.
Yeah.
Something about the action space needing to encompass the parameter space.
Yes.
What does that even mean?
That's a great question, and it's a crucial point.
Okay.
Essentially means that for any possible value of the unknown parameter theta, remember those are the hidden factors driving the outcome.
Okay.
There's an action you can take that directly corresponds to it.
So it's like having a tool for every job.
Yes.
If you're trying to figure out the best ad to show, you need to have a wide enough range of ads to choose from.
Exactly. If the action space doesn't encompass the parameter space, things get trickier.
Oh, no.
And that's where this notion of fragility dimension comes in.
Fragility dimension.
Yeah.
That sounds delicate.
Well, it can be.
Oh.
It's all about how robust your learning process is. If the actions you can take don't match up well with the true complexity of the problem, learning becomes much harder.
Okay.
You might end up stuck in a loop. Constantly trying things that just don't give you enough information.
So it's like trying to solve a jigsaw puzzle with some of the pieces missing.
That's a great analogy.
Yeah.
And the researchers point out that if the action space doesn't encompass the parameter space, you can't get a regret bound.
Okay.
That's both efficient, meaning it doesn't grow too quickly, with the complexity of the problem. And accurate. Meaning it doesn't give you too much wiggle room.
I see.
So this fragility dimension is a kind of warning sign telling us to be careful when applying Thompson sampling. We need to make sure our action space is rich enough that we have enough options to explore the full range of possibilities.
So this leads to some really interesting open questions.
It does.
Like what happens when the action space doesn't neatly encompass the parameter space?
Yeah.
Can we modify Thompson sampling to make it more robust in those situations?
Yeah. Good question.
Or do we need to develop entirely new algorithms that can handle these more fragile scenarios?
Potentially.
It's like this paper opens up a whole new world of questions and possibilities.
It does.
It doesn't just give us answers.
Right.
It pushes us to keep exploring and pushing the boundaries of what we know.
Exactly.
But before we go too far down that rabbit hole, I want to circle back to this idea of the information ratio for a moment.
Okay.
It seems like such a central concept.
It is.
In understanding why Thompson sampling works so well.
It absolutely is.
Yeah.
And the way the paper defines it is really elegant.
Okay.
It's the ratio of the squared expected regret, how much worse we might do because we're learning to the mutual information between the optimal action and the outcome.
So it's basically a measure of how much we're willing to sacrifice in the short term to gain knowledge that will benefit us in the long run.
Exactly. It's a trade-off.
Got it.
Between immediate gratification and long-term success.
Okay.
And the paper's key result is proving that this information ratio can be bounded by a value that only depends on the dimension of the problem.
So as the problem gets more complex, the amount of information we need to gather doesn't necessarily explode.
It doesn't have to.
That's pretty amazing.
It is.
How does that even work?
It's all thanks to some clever mathematical analysis.
Okay.
The researchers used some sophisticated tools
right.
to show that even though the relationship between the actions and the outcome is described by this logistic function,
yeah.
the information ratio
right.
can still be tamed.
So even though the problem might look messy on the surface,
right.
there's this underlying structure
yeah.
that Thompson sampling can exploit.
Precisely. And it's the structure
okay.
that allows it to balance exploration and exploitation.
Right.
So effectively leading to surprisingly low regret.
It's fascinating how these theoretical insights can translate into such practical power.
It is.
Yeah, it really shows the power of good research.
It does.
But I want to go back to that beta barrier idea for a second.
Sure.
The paper emphasizes how sensitive regret can be to that beta parameter.
Right.
The slope of the logistic function. I still find it strange that a steeper slope, a larger beta, actually makes it easier to find the best choice.
Right.
You'd think a gentler curve would be less punishing.
It seems counterintuitive, but remember,
yeah.
a steeper slope means a sharper contrast between good and bad choices.
Okay.
It's like having a spotlight shining directly on the best option, making it stand out more clearly from the rest.
So instead of wading through a sea of meh options,
exactly.
you quickly get a sense of what works and what doesn't.
Yeah.
But how do we actually know this?
Right?
Is it just a hunch, or is there some mathematical proof behind it?
It's not just a hunch.
Okay.
The paper proves that the regret bound for Thompson sampling in these cases is only logarithmic in beta.
Okay.
This means it grows much slower than previous bounds, which were way more sensitive to those high beta values.
So as beta gets bigger, as that reward curve gets steeper,
right.
the regret doesn't spiral out of control.
Exactly.
Thompson sampling can handle it.
It demonstrates just how robust the algorithm really is.
That's pretty amazing.
Thompson sampling can tackle a wide range of logistic bandit problems, regardless of how steep that reward curve is.
It's like it has this built-in adaptability.
Yeah.
Ready to handle whatever curveball the data throws at it.
Exactly.
Well, we've covered a lot of ground today.
We have.
Logistic bandits.
Yeah.
Thompson sampling. Regret, information ratios, fragility dimension, even the nitty-gritty of that logistic function itself.
Yeah, the whole 9 yards.
Before we sign off,
yeah,
what are the key takeaways you want our listener to remember?
I think the biggest takeaway is that Thompson sampling is a remarkably powerful and surprisingly adaptable tool for tackling a whole range of decision-making problems.
That's great.
It's not a one-size-fits-all solution, though.
Right.
Understanding the structure of the problem is crucial.
Okay.
What actions can you take? What hidden factors are driving the outcome?
Right.
How well do those two things line up?
It's all about making sure Thompson sampling has the right tools for the job.
It is.
And this paper really does a great job of showing both its strengths and its limitations.
Yes.
Giving a much clearer picture of its potential.
Absolutely. And what's truly exciting
yeah.
are the open questions it raises.
Like what?
How can we tweak or extend Thompson sampling to handle situations where those action spaces and parameter spaces don't perfectly align?
Right.
Are there other kinds of bandit problems where this type of analysis could give us new insights?
So many possibilities.
There are.
It feels like this research is just the beginning of a very exciting journey of discovery.
I agree.
Well, thank you so much for joining us for this deep dive.
It's been a pleasure.
We'll see everybody next time.